So precipitation reactions is a type of reaction in aqueous solution. And basically, it is kind of exactly what it sounds like. A precipitation reaction also is a type of metathesis or double displacement reaction. There are other names for this, but this is one type of reaction that follows the form AB plus CD gives you AD plus CB. So you're switching the negative ions in this precipitation reaction, and these are done with ionic or electrolytes, let's say, and it results in the formation of a solid. So, for instance, you're mixing two aqueous solutions, and what you're getting is a solid, and then usually another aqueous salt. And the solid is what we call the precipitate. It's what precipitates out of the solution. And in order to determine whether something is going to precipitate or not, you have to follow what are called the solubility guidelines. These are not really things you can guess. Most of the time, you'll be given them to look up, but what's important is you know how to read the solubility guidelines. So here's what they look like. So for the soluble ions, the normal rule is that they are aqueous, and then the exception is that they are insoluble. So for instance, alkali metals, any salt made with an alkali metal, ammonia, nitrate, acetate, chlorate, or perchlorate, for our purposes, are always going to be soluble. So anything you see, any salt you see that has any of the alkali metals, lithium, sodium, potassium, etc., the ammonium ion, nitrate, acetate, chlorate, or perchlorate will always be soluble. So let's say, sodium chloride, lithium hydroxide, magnesium nitrate. Okay, you see sodium, you see lithium, you see nitrate, you say, okay, that's guaranteed to be soluble, so we'll put aqueous. Okay. The halogens, fluorine, chlorine, bromine, and iodine, are usually soluble with a few exceptions, and those exceptions are silver, lead 2+, and mercury 2+. So something like magnesium fluoride would be soluble, aqueous, but lead fluoride would be solid. Okay, so because it's an exception to the rule, and the rule is that it's usually soluble, it's insoluble, and we write that as solid. Sulfate, same thing, although it's got a couple more exceptions. So, for instance, if you had magnesium sulfate, that would be soluble. But calcium sulfate is solid. So, it basically, if it is not one of the exceptions, then it's soluble. Okay. Next, I skipped it. There we go. So insoluble ions, these ones are usually insoluble, and the exceptions are soluble. So carbonate, phosphate, chromate, and sulfide are usually insoluble. So if you had, I'm using magnesium just as a baseline, right? Magnesium carbonate, that would be solid. Any of the alkali metals and NH4 would be magnesium carbonate is insoluble, so it's solid. The exceptions, alkali metals, would be soluble. So lithium carbonates would be aqueous. Hydroxides are mostly insoluble, so magnesium hydroxide would be insoluble, and so it's a solid. Then, again, the alkali metals and barium, and I believe strontium as well. 2+. So, barium hydroxide. Right, so if you had barium hydroxide, that would be aqueous. And so what you do is when you look at an ionic compound, you look up these rules and you say, okay, is this aqueous? Is this solid? If it's soluble, it's aqueous. If it's insoluble, it's solid. So, for instance, sodium chloride. Well, we look up the guidelines and we see, okay, sodium 100% of the time is soluble, so this is soluble, aqueous. Silver chloride. We look up chloride is usually soluble except for silver, so silver is an exception to the chloride rule. So the exceptions for a soluble compound are that it's insoluble, so silver chloride is solid. Magnesium hydroxide. Hydroxides are usually insoluble. Magnesium is not an exception, so it follows the rule for insoluble compounds, so it's solid. Lithium hydroxide. Lithium is an alkali metal, so the hydroxide being insoluble, it has an exception in lithium, so this is exception to the insoluble rule, so it's soluble, so it's aqueous. And this is what you do. So you look at a reaction and you say, okay, magnesium chloride, look it up, it's soluble, so we write aqueous. Sodium hydroxide, we check the charts, aqueous. Sodium chloride, check the charts, aqueous. Magnesium hydroxide, check the charts, solid. So then we'd say, okay, this is a precipitation reaction. Okay? So here are the solubility guidelines for you to reference. If you have the slides open, then you can look at those. But let's do some practice. So, lithium perchlorate. Well, if you look it up, both of those, lithium, alkali metals, always soluble. Perchlorate, always soluble. So it's like double always soluble. So it's soluble. So it'd be aqueous. Calcium carbonate. We look at carbonate, usually insoluble. Calcium is not an exception, so it'd be insoluble. So it's solid. Ammonium phosphate. We look at phosphate and we see, okay, phosphate is usually insoluble. Exceptions are ammonium. Ammonium is an exception. So although it's usually solid, in this case it's going to be aqueous, soluble, because it's an exception. And finally, lead fluoride. We can look up fluoride. It's usually soluble, but lead is an exception, so it's going to be insoluble or solid. Then the next thing we want to look at precipitation reactions are what's called the net ionic equation. Okay, and the net ionic equation is basically, here's what actually happened. Here's the reaction that actually occurred. Okay, so in order to get to the net ionic equation, what you do is you write out the balanced molecular equation. For instance, magnesium chloride plus 2 silver nitrate gives you magnesium nitrate plus 2 silver chloride. And you'll notice I have the states there. So magnesium chloride's aqueous, silver nitrate's aqueous, magnesium nitrate's aqueous, silver chloride solid. Okay, that's the molecular equation. Then the next thing you write out is you write out the complete ionic equation by splitting the aqueous compounds into ions. So for instance, magnesium and chloride becomes 1 magnesium 2 plus and 2 chloride minus. You'll note that it is not, right? This does not split into magnesium 2 plus Cl2, okay? That is incorrect. This is 2 chloride ions. You put magnesium chloride in water, and you get 1 magnesium 2 plus and 2 chlorides, Cl minus, okay? You don't get a Cl2. It's 1 magnesium and 2 chlorines, okay? So that splits into its ions. Silver nitrate will split into its ions. And so it's 2 of 1 molecule, so there's 2 silvers and 2 nitrates. Okay, 2 silvers, 2 nitrates. And then on the right side of the equation, we do the same thing. Magnesium nitrate splits into ions, so 1 magnesium, 2 nitrates. And then silver chloride is solid. Any solids, liquids, gases stay as solids, liquids, and gases. So that we just write down at the same. Okay, so this is solid, so it stays solid. All right. I forgot to put some of the aqueuses in here. It doesn't actually, in my opinion, it doesn't matter if you write aqueous here, because since we're writing them as ions, they have to be aqueous. So I don't think you need to write aqueous, but if you're doing like an online homework system, it might complain if you don't put aqueous. But if it's an ion, it has to be aqueous. Okay, so then that's the complete ionic equation. So then to go from the complete ionic equation to the net ionic equation, what we do is we cancel ions that are the same on both sides. So for instance, here I've got 2 chloride minus, and here the chlorine is in solid silver chloride. So that did something. But I've got magnesium 2 plus here, and I've got magnesium 2 plus there. So those are going to cancel out. I've got 2 nitrate here, and I've got 2 nitrate here. So those are going to cancel out. Okay. So the silver and the chloride end up in a solid. So they changed state. So they're going to be different. Okay. So then when I rewrite that, I have 2 chloride plus 2 silver gives me 2 silver chloride. And that's my net ionic equation. In essence, this is what actually happened. And then the magnesium and the nitrate, the ones that canceled out, are what are called my spectator ions. They did not participate in the reaction. They did nothing because although in the molecular equation, right, we have, oh, I made magnesium nitrate. You didn't, though, because if we were to look at a beaker, right, okay, I've got magnesium 2 plus, I've got chloride minus, right, and I'm pouring in silver, my silver nitrate solution. Right? And then when I look after the experiment, after I've mixed them, what I see my solid silver chloride will collect at the bottom. And then I've got magnesium ions and I've got nitrate ions. Right? So these guys, the magnesium and the nitrate, did not do anything. They were dissolved as ions, and they're still dissolved as ions. So they don't participate. Okay. So let's look at another example. A solution of sodium hydroxide is combined with a solution of iron 3 chloride, and a white precipitate, iron 3 hydroxide, forms. Write out the molecular, complete ionic, and net ionic equations, and give the spectator ions. All right, so first things first, we need to write our balanced chemical equation. So sodium hydroxide is NaOH. Iron 3 chloride is FeCl3. And iron 3 hydroxide is FeOH3. Okay? So my molecular is going to be 3 sodium hydroxide plus iron 3 chloride gives me iron 3 hydroxide plus 3 sodium chloride. Okay, so now everything that's aqueous, okay, I'm going to split up into ions. So remember, I'm going to have 3 sodiums, 3 hydroxides, 3 chlorides, right? So, complete ionic, 3 sodiums, 3 hydroxides, 1 iron 3 plus, and 3 chloride minus, right? Then on this side, 3 sodium plus, 3 chloride minus, okay? So, this stays the same, right? Because it's solid, so I don't change that. Okay, so then moving to the net ionic, right? I've got sodium plus, 3 sodium plus, so those are going to cancel out. I've got 3 chloride minus and 3 chloride minus, so those are going to cancel out. My iron and my hydroxide are combining to form a solid, so they're actually participating in the reaction. So my net ionic, I'm just going to write that down. I usually like to write the positive ion first, so I write that as iron 3 plus 3 hydroxide minus gives me iron 3 hydroxide solid. And then my spectator ions are going to be my sodium and my chloride because they didn't do anything. Oops. So that's how you go about doing that from a word problem. So let's do some practice. A solution of sodium phosphate is mixed with a solution of copper 2 chloride, and a blue precipitate copper 2 phosphate forms. So I write the molecular equation. So again, we'll go up here and we'll say, okay, sodium phosphate is Na3PO4. Copper 2 chloride is CuCl2. And copper 2 phosphate is Cu3PO4 2. So the molecular equation is going to be 2 sodium phosphate plus 3 copper chloride, giving me copper phosphate, 1 copper phosphate, solid, plus 6 sodium chlorides. Okay? Then the complete ionic equation, okay, so that's aqueous, that splits up. So keep in mind, I'm going to have 6 sodiums, 2 phosphates, 3 coppers, and 6 chlorides, right? And then this is going to stay the same. So 6 sodiums plus 2 phosphates plus 3 coppers plus 6 chlorides gives me 1 copper phosphate solid, 6 sodiums, and 6 chlorides. So then the net ionic, 6 sodiums on both sides, 6 chlorides on both sides, so those cancel out. So it's just going to be 3 coppers plus 2 phosphates gives me 1 copper phosphate. And then my spectator ions are going to be the ones that cancel out, sodium and chloride.